Okay, good morning. So we will continue our discussion from the previous class. We had just started discussing about simple Brayton cycles or simple gas turbine cycles. Okay. And then in the subsequent classes, starting from today, we will see how to modify these cycles to achieve better work output and better efficiency. Okay. So for this simple Brayton cycle, standard Brayton cycle, we had taken some assumptions like constant CPCV, no change in mass flow rate, isentropic processes, no frictional losses like this. And we did an analysis. By the way, can you see my screen?
Yes, sir.
Okay. So we can draw the cycle in a TS diagram like this. So 1 to 2 is the isentropic compression process in the compressor. 2 to 3 is the constant pressure heat addition in the combustion chamber. 3 to 4 is the isentropic expansion in the turbine. And 4 to 1 is a hypothetical constant pressure heat rejection, just to bring the or close the cycle from 4 to 1. Okay, it's a constant pressure process. And we can easily analyze the cycle if we assume that the Cp remains constant. All the enthalpy changes can be written in terms of Cp into delta T. And with this, we had found that efficiency can be written as 1 minus 1 by R to the power gamma minus 1 by gamma, where R is the pressure ratio, or compression ratio, okay, which is a important design parameter. Then we had also seen how this efficiency varies with R. It is zero at it is zero when there is no compression. So compression ratio is 1, and then it increases gradually with increasing compression ratio. We had also defined another parameter which we called as non-dimensional net specific work output to see how the work output varies with the design parameters. And we found that the work output varies with the not only with the compressor pressure ratio but also with the temperature ratio, which we had defined as the maximum temperature in the cycle T3 by the minimum temperature in the cycle T1. Okay. So, and it varied like this. So for a particular T value, the net work output increased with R up to a certain point and again decreased. So there was an optimum point where the value is maximum. Similarly, for T is equal to 3, again it increases and decreases. I have shown you some plots in MATLAB also, where you can see actually they start decreasing, although the decrease is quite gradual. It is not a very sharp decrease. For T is equal to 4, 5, 6, all cases it will decrease, but the decrease will be quite gradual for higher values of T. And we found at what value it becomes 0. For example, for T is equal to 2, we can just fit the value in the expression for non-dimensional work output that T is equal to 2 and equate it to 0 and find out what is the value of C for which the work output is 0, and it was found to be 2 for T is equal to 2, which means a pressure ratio of 11.31. C, remember, C is R to the power gamma minus 1 by gamma. This is just a way of writing in because we encountered this term many times, right? Okay, so let us try to understand this better. That why there is a peak value and why again this decreases the work output. Okay, why the work output starts increasing, why there is a peak value, and why it starts decreasing. Okay, for all the cases it is there. Let us consider again this simple Brayton cycle. Okay, what we are going to do is we are going to assume that the T1 is fixed due to ambient conditions, which is a reasonable assumption. Ambient conditions are fixed, and T3 is fixed because of the turbine blade limit. Okay, turbine blade material and cooling. So it depends on the turbine blade. So T1 and T3 are fixed. Both are reasonable assumptions. Now, if we have a very less pressure ratio, the cycle will look like this. Let me just explain it here in a better way. Okay. So if the compressor pressure ratio is very small, this point is 1 obviously, and this will be 0.2. Okay, very small change is occurring because very small pressure ratio is there. So T2 by T1 will be very small. Okay, T2 by T1, which is equal to R to the power gamma minus 1 by gamma, is now small. So the cycle will look like this blue color cycle. Okay, my drawing will be very difficult here with the mouse, but you have to follow this line. Okay, this blue colored cycle. This narrow thin cycle, it will look like this. Obviously, by looking at it, we can understand that the work output is very less. What is the work output of the cycle graphically? It is the area within the cycle, right? So the area within the cycle is very small. As a result, the work output is small. At the limit when R is equal to 1, compressor pressure ratio is 1, T2 by T1 will become equal to 1. So T2 will be equal to T1. So both this top line and the bottom line will coincide, and we will be left with zero area inside the cycle. So zero work output. So for R is equal to 1, we have zero work output, as we have seen in the plot also. Then if we keep on increasing the pressure ratio, what happens? You keep on increasing T2 by T1. Okay. So maybe we will reach a point like this, and then the cycle will go from this point to this point somewhere around here. It will come down like this, and it will close like this. Okay. So you can see that the area within the cycle is increasing, keeping T1 and T3 fixed, but increasing R. Okay. So at some point, the area will become largest within the cycle. It means that at that R, the work output is maximum. Okay. At that value of R, the work output is maximum. And then if you keep on increasing the value of R, what will happen? Because this T2 is becoming very close to T3, you have a very less heat addition process. So again, it will become thin, but now in the vertical direction. Instead of this direction, it will become thin in the vertical direction. So say I have a very large value of pressure ratio. Okay. So I have a cycle like this. Very thin and very narrow. Okay, very thin and very narrow cycle. So again, the area is reduced. It means that again, the work output gets reduced. And at the limit, when T2 is equal to T3, so for a pressure ratio where T2 becomes equal to T3, then there is no more, like, then the T2 and T3 points will coincide, and the area within the cycle becomes equal to 0 again. So it means that there is no work output. Although the efficiency is very high at that limit, the work output goes to 0. Okay. Heat input also goes to 0. So you cannot directly measure the efficiency there. But theoretical efficiency is quite high. But the work output goes to 0. Is this clear? Why there is an optimum point of work output? Like there is an optimum value of R where the work output is maximum. That is what we are seeing also in the plot, that at some value of R, the work output is becoming maximum. Now the question is, what is this value of R for which the work output should be maximum? Okay. We can find that easily. So if we assume that T1 and T3 are fixed, there is an optimum value of R for which the W net is maximum. So this is the expression for W net by CPT1. Okay. W net by CPT1 is equal to T into 1 minus 1 by C minus C minus 1. So this same expression. Okay. So assuming constant, we can write, we can find the optimum value, maximum work output, if we take a derivative of this net work output term with respect to R, okay, and equate it to 0 to find the maximum value. So DDR of this W net by CPT1 equal to 0 will give us the maximum work output, because we have seen graphically that there is a value of R for which the work output is maximum, okay, not minimum, it is maximum. So this also means that we can just we can do the derivative in terms of C, because for the unique value of R, there will be a unique value of C. So DC of W net by CPT1 equal to 0. Okay. And if you take a derivative of this term with respect to C, you will get. So this term will give you minus T by C square, this first term, and this will give you -1. Okay. The other terms are 0. So which means that T by C square is equal to 1, or C is equal to root T, or R is equal to T3 by T1. Let me keep the diagram open. R is equal to T3 by T1 to the power gamma by 2 gamma minus 1. Okay. So this is the point. For this value of R, you get the maximum work output. Let us try to understand this better physically. Okay. So C is equal to root T, or C square is equal to T. Okay. So what is C? C is R to the power gamma minus 1 by gamma. So C is nothing but T2 by T1. Okay. Because T2 by T1 is R to the power gamma minus 1 by gamma. C is also equal to T3 by T4, because T3 by T4 is also R to the power gamma minus 1 by gamma. And these things we have seen. So you must read before the class the previous day's material so that you can understand what we are discussing. Otherwise, you will not remember these things. Okay. Just you will be vaguely looking at the screen. So if you had read last day's material, you will know that, like what I am saying, without going into checking the notes. So before, it is very beneficial before each class, if you have a quick go through the class notes for that class, previous class. Okay. So T2 by T1 is R to the power gamma minus 1 by gamma, which is equal to C. And T3 by T4 is R to the power gamma minus 1 by gamma, which is also equal to C. Okay. So this C square I can write as T2 by T1 into T3 by T4. This is equal to the temperature ratio T3 by T1. Okay. So from this expression, we find that T2 is equal to T4. So T3 and T1 gets cancelled, T2 is equal to T4. Now it is clear to us physically what is the point at which we get maximum work output. T2 equal to T4 means these 2 points are at same temperature. Okay. So these 2 points and 4 points are at the same height. They are at the same temperature. So when this will happen, we will have the maximum work output. Okay. So for a cycle, somewhere around here, okay, maybe T2 and T4 will become equal, and at that point we'll have the maximum work output. You can find out what is the maximum work output in terms of the expression by replacing the optimum value also. Any questions? Just one final thing to note here is that you can see that the optimum R value or optimum C value will depend on what? On the temperature ratio. So if when the temperature ratio increases, so we have seen that for 2, the optimum value is less. For T equal to 3, it increases. For T equal to 4, it increases. So the optimum value keeps on increasing because it is equal to square root of T. So C is equal to square root of T, and from C we can calculate what will be the R value. Okay. So let us then continue to the next type of cycle. Okay. I hope this was clear, because this you have already studied Brayton cycle, very basic thermodynamic cycle, one of the fundamental thermodynamic cycle. So now there are 2 questions: how to increase the efficiency of the cycle, and how to increase the work output from the cycle. because these are two separate things, separate parameters, right? So work output is, even with without increasing the efficiency, if we can increase the work output, it is beneficial. Work output is net specific work output, because then we will have lower cost, because mass flow rate will be lower and all the size will also scale down. On the other hand, just a second, please. Yes. So on the other hand, if we want to increase the efficiency, that is also beneficial, of course, because you need less amount of fuel to generate the same amount of power. So both are beneficial. Okay. So we will see modifications to increase each of them, the efficiency as well as the net specific work output. So the first modification that we will consider is gas turbine cycle with regeneration, or Brayton cycle with regeneration. So if we see the standard Brayton cycle, the first thing we can easily notice in the cycle is that the exhaust gas goes out at quite a bit of high temperature. Okay, the ambient temperature is T1, maybe it is 300 Kelvin, but the exhaust gas, obviously, looking at the graph itself, it is clear that it will be always at a much higher temperature, much higher than T1, much higher than the ambient temperature. So lot of heat is getting carried away by the exhaust gas, which is dissipated to the atmosphere, which is unused. Okay, if we can somehow use that, some portion of that heat, some portion of that energy, then it will be much more beneficial, okay, to increase the efficiency. So this is the idea behind the regenerative cycle, okay, regeneration cycle. So the idea is that the exhaust gas which goes out at state 4, okay, will be used to heat up some of the air which is coming from the compressor. Okay, I will explain the cycles in a minute, but let me first explain the philosophy. The philosophy is that we have lot of heat which is getting wasted in the exhaust gas. As part of the exhaust gas, we'll use some part of that heat to increase the temperature of the air which is coming from the compressor. If the temperature is increased, of temperature of the air coming from the compressor is increased by this process, the heat addition that will be required in the combustion chamber will be lower. As a result, we will need less fuel input in the cycle, and the efficiency, work output will remain same, efficiency will increase as a result. Okay, so this is the idea behind this. So with this modification, the cycle looks like this schematic diagram. So you have the compressor again, and compression process going from 1 to 2. So from 2 to 5, we have heat increase, temperature increase at a constant pressure in a heat exchanger. Okay, temperature of the air increases at constant pressure. So similar to the combustion process, but without combustion, due to heat exchange, it is increasing. Temperature is increasing. So it increases from 2 to 5 in a heat exchanger. Then from 3 to so from 5 to 3 is the combustion process in the combustion chamber. From 3 to 4 is the expansion in the turbine, and from 4 to 6, the exhaust gases flow through the same heat exchanger, where it loses its energy for heating this air from 2 to 5. Okay, so the heat loss from 4 to 6 is equal to the heat gain from 2 to 5. We can write in terms of enthalpy, if we assume the same mass flow rate, H4 minus H6 is equal to H5 minus H2, or Cp T4 minus T6 is equal to Cp T5 minus T2, or T4 minus T6 is equal to T5 minus T2. Okay, so based on energy balance in the heat exchanger, if it is a ideal heat exchanger. So now if you look at this cycle, it is apparent, it is very clear that this can only be done, this regeneration process can only be done if this 0.4 is above this 0.2. Okay. If the exhaust gas temperature is below the compressor outlet temperature, then obviously you cannot have this temperature because it is already lower than 2. You cannot have heat exchange from the exhaust gases to the compressor outlet, to the air which comes out from the compressor. Okay, actually the opposite direction heat transfer will occur, and that will be detrimental to the cycle efficiency. So this is only possible, regeneration is only possible and beneficial if T4 is higher than T2. Okay, can only be if T4 is higher than T2. Now, if the heat exchange process is ideal, okay, ideal means full heat exchange can occur. Okay, there is unlimited time available, infinite time available, and infinite surface area for heat exchange theoretically. Then theoretically, the maximum temperature that can be reached for this compressor outlet air is equal to the temperature of the exhaust gases. Okay, this is like a counterflow heat exchanger, and the maximum temperature at this point which we can reach is equal to the temperature at this point. Okay, so the maximum temperature theoretical limit is given by 5 dash. Okay, in this diagram, so 5 dash T5 dash is equal to T4. Okay, this is the maximum temperature that can be reached. But in real life, what will happen? Because the surface area of the heat exchanger is limited, and we have a limited time for heat transfer to occur, we will not be able to reach the maximum temperature. We will reach somewhat lower temperature. Okay. So similarly, in the other direction also, the minimum temperature that can be reached in the case of ideal heat exchanger is 6 dash, which is equal to T2. T6 dash is equal to T2. But in real life, what will happen again? Because we cannot have infinite surface area of heat exchanger and infinite time available for heat exchange process, we will reach somewhere above 6 dash point. So we'll reach T6, which is slightly higher than T2. Okay. So points 5 dash and 6 dash denote a heat exchanger regenerator with 100% effectiveness. In actual applications, we will be somewhere below 0.5 dash, which is denoted by 0.5. Okay. So therefore, in real life, T5 is less than T4 and T6 is greater than T2. We have already discussed this. Just keep it open here.
Sir,
Yes.
sir, in real life, do we
Yes.
want to have a higher temperature inlet air for combustion or slightly less?
I could not understand. Can you repeat
So,
your question?
in case of IC engines, after turbocharging the inlet charge,
Hmm.
we put an intercooler
Hmm.
to reduce the temperature.
Hmm.
So, is it ideal if we have a higher temperature of air to the combustion chamber?
Uh, it's there is no harm unless it. So if you are increasing, see what is happening in the cycle from cycle thermodynamic point of view. You see, uh, the work output is not changing. Okay, so work output. What is the work output? CPT3 minus T4 minus CPT2 minus T1. Right. So the work output is not changing in any way. So the only change
Combustion
that
fuel
combustion
is
process, only change that will occur is the reduction in fuel for the combustion. Okay, amount of fuel that is required for combustion, because already you are heating the already you are increasing the temperature. Okay, so because you are already increasing the temperature, your change in temperature that needs to occur in the combustion chamber is much less. As a result, you need less external heat addition and your efficiency increases. So this is always beneficial if T4 is higher than T2. Okay, your turbocharging process is a very different process. Turbocharger is not there to increase. Its role is not to increase the temperature. Okay, here the role itself is to increase the temperature. Turbocharger is there to increase the intake air, amount of intake air. If without any supercharger or turbocharger, there is a certain amount of intake air. A turbocharger or supercharger compresses the air and increases the amount of intake air. So which is much more beneficial. So that is the actual role there. Okay, so it is incidental that the temperature increases there, but here the role is to increase the temperature in a regenerator.
Okay, sir.
So yes, so we can define a parameter which is called as regenerator effectiveness. Okay, this is given by this epsilon is equal to H5 minus H2. Okay, let us look at this diagram. H5 minus H2 by H5 dash minus H2. Okay, so ideally we know that the uh, change in enthalpy that should occur is H5 dash minus H2, but in real life, which we are getting H5 minus H2. Okay, so the theoretical limit is 1 when when 5 becomes equal to 5 dash. Okay, so this can also be written as assuming constant Cp. This can also be written as T5 minus T2 by T5 dash minus T2. Because we know that T5 dash is equal to T4, we can write this as T5 minus T2 by T4 minus T2. Okay, this is the heat exchanger or regenerator effectiveness. Typically, it is between 85 to 90%. Okay, this effectiveness is between 85 to 90%. This can be increased if you use a larger heat exchanger area, means larger regenerator, but that will increase the cost and pressure drop in the heat exchanger. Okay, which is again not good. Here we are reading about ideal cycle, but in actual cycle there will be a pressure drop in this part. So it will reduce the work output from the turbine. So this is a typical value. Okay. So now for this Brayton cycle with regeneration, what is the efficiency? Let us try to find out. So again, the efficiency is equal to the net work output, which is Cp T3 minus T4 minus Cp T2 minus T1. The work output remains same as the simple Brayton cycle. No change is occurring in the work output. However, the heat input is now changed. Instead of Cp T3 minus T2, it is now Cp T3 minus T5. Okay, Cp T3 minus T5. So we will do the analysis for simplification. We will do the analysis with for the ideal cycle with a heat exchanger effectiveness of 1. Okay, where T5 is equal to T4. For the real cycle, we will later be able to incorporate the heat exchanger effectiveness in the equation and plot the results. But at this point, let us assume that we have a 100% effective heat exchanger. Okay. So in this case, for T5 is equal to T4, and we can write this efficiency as T3 minus T4 minus T2 minus T1 by T3 minus T4, which is, if you simplify, which is equal to 1 minus T2 minus T1 by T3 minus T4. If you take T1 by T3 common, if you take T1 common from the top, you get T2 by T1 minus 1, and from the bottom, from the denominator, if you take T3 out, you get 1 minus T4 by T3. So this is equal to, so T2 by T1 we know is equal to C, which is R to the power gamma minus 1 by gamma. And T3 by T4 is also equal to C. Okay, so T4 by T3 is equal to 1 by C. So this is equal to 1 minus 1 by T, C minus 1 divided by 1 minus 1 by C. If you take out C as common, the numerator and denominator both become same. So if I take C common, it will become 1 minus 1 by C. Denominator is already 1 minus 1 by C. They cancel each other. So we are left with eta is equal to 1 minus C by T. So this is the expression for ideal Brayton cycle with regeneration efficiency. Okay, efficiency for ideal Brayton cycle with regeneration. So which can also be written as 1 minus R to the power gamma minus 1 by gamma divided by T. Okay. So here you can see that one first distinction is that here in the expression, the T also comes into the picture. Okay. Unlike the Brayton cycle. What was the expression for the Brayton cycle? The expression for the Brayton cycle only had R, right? Only had R. 1 minus 1 by R to the power gamma minus 1 by gamma. There was no T there. But now for regeneration, T is also important. So if the value of T increases, this negative term will decrease. So 1 minus the negative term will increase, so efficiency will increase. So by increasing T, we can increase the efficiency. Second is that here you could not increase the efficiency by increasing T. Efficiency was fixed. It was independent of T. But for regeneration, we can increase the efficiency by increasing T. If we increase the value of R, okay, strangely, if we increase the value of R, this negative term value will increase. So 1 minus this negative term will decrease. The efficiency will actually decrease with increasing pressure ratio, which is very different behavior, the totally opposite behavior as compared to simple Brayton cycle. In simple Brayton cycle, we have seen that with increasing R, the efficiency increases. In this case, with increasing R, the efficiency decreases. Okay, so for lower value of R, we have higher efficiency. This looks like this. Okay, this plot looks like this. So for each value of T, for example, for T equal to 3, the plot for the theoretical limit for R is equal to 1 is a very high value, and then gradually the efficiency keeps on decreasing with increasing R. Okay. For a higher value of T, again we will have the same pattern, but the efficiency values will be higher, but it will again decrease with increasing R. Similarly, for T is equal to 5. What is the limit at R equal to 1? So you can just put R equal to 1 here and find the limit. So eta will be equal to 1 minus 1 by T. So for T equal to 3, eta will be 1 minus 1 by 3. So it will be 2 by 3, 66.67%. Similarly, for 4, it is 1 minus 1 by 4, so 0.75. So this value will be 0.75. Obviously, at this point, you cannot operate the cycle. Why cannot we operate the cycle at this high efficiency point or very near to the high efficiency point?
So like because there is no like pressure difference, so like the flow will not occur.
So the flow occurs. What happens? Slowly flow is occurring. Small, like just slight pressure change we are giving. Still, we will not be working in that range. Okay. Slight compressor, say it is 1.2, say. Still, the efficiency is very high. So still, what is then the harm in operating with this high efficiency with a pressure ratio of 1.2? You have to think logically. We have already explained this, discussed this in detail yesterday and today.
Turbine work will be very small.
The work will be very small. Yes, overall work itself, the cycle will be very small, right? We have seen that just
The
now
cycle
itself,
will be a line almost.
almost like a line. So the area within the cycle is very small. It will be like this narrow one. Okay. So although the efficiency can become very high, but the work output is too small. So it is nowhere near the optimum work output. That's why it is not. It cannot be used at that point. Okay. So that you have to think logically. We have already discussed this also. So if you keep on increasing the value of R, then the work output increases up to a certain point, again it decreases. Remember, the work output is independent, whether it's a regeneration process or simple Brayton cycle. We have already shown that the work output does not depend on that. The work output, the T3 minus T4 and T2 minus T1 values remain same for this cycle. It's only that the heat addition is changing. The work output is same for both the regeneration cycle and the simple Brayton cycle. Okay, only the efficiency is changing. So now we have seen that efficiency increases with increasing temperature ratio and it decreases with increasing value of R. So tell me now why this is happening. Why it is happening? Say if I have a fixed R, then why this efficiency is higher with higher temperature ratio? And if I have because it was not the case for simple Brayton cycle. Here if I had a fixed R, the efficiency was fixed. it was not changing with temperature ratio. But in our case, now it is changing with temperature ratio. So why is the efficiency increasing with temperature ratio for a fixed R? What is the physical reason behind this? Not the mathematical one. Answers. Any answers? You have to think logically. You are not thinking logically, all of you. Everything is connected, right? What is the benefit of having higher temperature ratio for a regeneration cycle? Keeping R constant. Or let us go to the other question first. Say T is constant, temperature ratio is constant. Okay. So why is the efficiency decreasing with increasing R? What is happening which is causing the efficiency to decrease with increasing value of R?
So the regenerate amount of fuel is going to increase.
Can you tell in a better way what is?
Heat addition during the combustion increases with increase in ratio.
Why does it increase?
So the compressor temperature after compressor is actually now closer to the exhaust gas after heat exchange.
So then,
So
so
sir, the
T2 is very, you are saying T2 is close to T4. Is it so? Then what is happening? You are in the correct track, but what you are not able to explain
so
clearly what.
heat exchanger won't be able to give much heat to the air.
Correct, correct. So that is what I am looking for. Means the scope for regeneration is decreased. Keeping T constant, if you increase R, T2 keeps on increasing, right? T2 keeps on increasing and T4 keeps on decreasing. Okay, if you increase R, keeping T3 constant because T is constant. So the difference between T4 and T2 dictates how much heat exchange can occur. If they are very near to each other, then they will not be able to, there will not be much scope for regeneration to occur. So the efficiency will actually keep on decreasing with increasing R for regeneration cycle. Now tell the other case what is happening if R is fixed but T is increased. Why the efficiency increases? It was not the case for Brayton cycle. So what has happened there?
Because the scope for regeneration, the temperature difference between T2 and T4 is increasing, sir.
Correct. So because your T3 point goes higher and this T2 minus T1 remains same. So T2 is at the same height. R is fixed and T3 goes higher means T4 also goes higher. So the difference between T4 and T2 increases. So scope for regeneration increases. So with increasing T, you get higher regeneration. Okay. Now by looking at this graph, we can see that it will keep on decreasing and there will be a certain point at which the efficiency will become equal to the simple Brayton cycle efficiency. And then it will go lower than that efficiency. Okay, the regeneration cycle. So after that point, it does not make any sense to use the regeneration cycle because the simple Brayton cycle without regeneration has a higher efficiency. So this value is actually higher for higher values of T and lower for lower values of T. Okay, because the cross section occurs at a low value of R. So physically, what does it mean? At what point will you think this will occur? At what point you think that there will be like the simple Brayton cycle is sufficient? There is no need for any regeneration. Physically, when will this happen in the cycle that these two efficiencies are same? I'm waiting for some answers.
Like I think when T like 2 and 4 points are parallel, then
Yes, correct. So if T2 and T4 becomes equal, temperature at point 2 and point 4 becomes equal, then there is no scope for regeneration. Okay. So that will become like a simple Brayton cycle. And then if with increasing, even if you further increase the compressor pressure ratio, T2 will go higher than T4 and heat exchange will occur in the opposite direction. And that means that actually it will be detrimental. It will be having lower efficiency. Okay. So more heat addition is required. So the limiting case where these points, where the blue lines touch the red line, is at T2 equal to T4 for different values of temperature ratio. Okay. What do we know? What else happens at T2 equal to T4?
The work done will be maximum.
Work done will be maximum. Okay. So at this point, the work done is also maximum. So generally, regeneration cycles we operate at slightly lower than optimum work output. Okay, slightly lower than optimum work output to get a better efficiency, and still the work output remains quite high. Okay, there is no point in going beyond this optimum value of work output because the efficiency will become lower for regeneration cycle. So somewhere around here, we will have high efficiency also and reasonable work output also. For R is equal to 1, we have explained eta is equal to 1 minus 1 by T. So this is equal to 1 minus T1 by T3. T1 is the minimum temperature in the cycle, T3 is equal to the maximum temperature. So this is like a Carnot cycle efficiency, this theoretical limit. Okay. So this optimum point, mathematically also we can find, or not the optimum point, when this becomes equal. So if C is equal to root T, okay, then eta is equal to 1 minus, so what was the expression? 1 minus C by T. So 1 minus C by C square. Okay. So 1 minus 1 by C or 1 minus 1 by R to the power gamma minus 1 by gamma. This is equal to the simple Brayton cycle efficiency. So the efficiency becomes equal to the simple Brayton cycle efficiency when this condition is satisfied, that C is equal to root T. And C is equal to root T happens when T2 equal to T4. We have already seen that. Okay. So we have already seen that C is equal to root T when T2 is equal to T4. So at T2 equal to T4, both the efficiencies become same because there is no scope for regeneration. As C is lower, whenever C is lower means R is reduced, efficiency increases as there is more scope for regeneration because T4 is greater than T2. All this we have discussed. This is just summarization. So for regeneration cycle, what happens finally to summarize? Efficiency increases up to a certain value for lower values of R, and but the net specific work output remains same as the simple Brayton cycle. Okay. Any questions? So let us again try to take a look at the graphs like the previous day's graphs. This is for the simple Brayton cycle. Okay. Efficiency. So we had seen yesterday that how it increases. So at compressor pressure ratio of 30, we are slightly larger than 60% efficiency for an ideal cycle. For regeneration, these are the lines. This is for T equal to 2. T is equal to 2, this limit is 0.5, right? 1 minus 1 by 2, so 0.5. So, and then it starts decreasing and you reach the equal value somewhere here. Okay, you can find it theoretically. T equal to 3, T is equal to 4, T equal to 5, and T equal to 6. Okay. So you can see that for higher temperature ratios like T is equal to 5 and 6, you have quite a large region where regeneration will be quite effective, like this area. I have to go to very high values of pressure ratio to actually go to a situation where the regeneration cycle has lower efficiency. If you operate somewhere around say 15 or 20, this is quite high efficiency plus reasonably high work output. So work output looks similar to the graphs that we have shown previously. Okay, no change happens in the work output. So the graphs are similar. They just depend on three values. These lines we will see later. So these are the work output if you remember from yesterday's class. So this is for t equal to 2, t equal to 3, 4, 5, 6. Okay. All the cases have an optimum value, but they gradually decrease very gradually. Okay. So if you compare with the red line here, all ignore the blue and green line. The red line here was the t equal to 6. Okay, the top red line. So you can see for t equal to 6, the graph is quite flat for the work output. So even if we operate at a lower ratio, say if I operate at 10, we'll have a very high efficiency theoretically if R is equal to 10. But the work output will not be much lower, okay, at R is equal to 10 because the graph is so flat. So we can find quite a bit of region where the efficiency is quite high, but the work output is not compromised much. Okay. So although the optimum value of work output occurs when there is the crossover point, okay. So crossover here is after 25 or something like that. So this is the around the optimum value of output, not clear from the graph. So this is the just gives you an idea about how actually it looks like. Just a second. It is the previous days. I'm just checking whether download and check attendance. Because I don't want to waste time in taking attendance. We can just take a look from here. I will be able to manage. Okay, so still some time is left. We will start the next cycle, okay, and then we will continue this in the next class. So the next modification to Brayton cycle is done to increase the work output. So we have seen one modification which is beneficial to increase the efficiency. Now we will see a modification which is done to increase the work output from the cycle. We'll see that it comes at the cost of efficiency. Efficiency is actually lowered with reheating. Unlike steam turbines, their efficiency is actually lowered, but the work output is increasing. So let us take a look at how the cycle looks like. Okay. So we have a compression process, compressor. Then we have the combustion chamber where the heat addition takes place. Then we have the expansion in the turbine. Okay. After expansion in the turbine, we do not expand in the turbine up to the inlet pressure. Okay, we expand in the turbine up to some intermediate pressure, and then we pass these products through a second combustion chamber. Okay, we pass these products through a second combustion chamber with additional fuel injection, where additional combustion happens, and again the combustion products are heated to a high temperature. So there is again more scope for extension of energy. Then in the other, there is a second turbine in which further expansion occurs and the combustion products go out at the pressure equal to atmospheric pressure, ambient pressure. Okay. So the first turbine is known as high pressure turbine or HP turbine. Second turbine is known as low pressure turbine or LP turbine. Okay. So the total pressure change from this 0.3 to 0.6 is equal to the pressure increase in the compressor. Okay. So these plots look like this in the TS diagram. T2 by, so compressor process looks like this. So from 1 to 2 isentropic compression. So from 2 to 3 is the constant pressure heat addition in the first combustion chamber. 3 to 4 is the isentropic expansion in the turbine, first turbine, high pressure turbine. And so it goes from pressure P3, which is equal to P2, to some intermediate pressure P4, which is below P2 but higher than P1. Okay, it is intermediate between P2 and P1. So it is intermediate between these two constant pressure lines. P2 to P3 is a constant pressure line. Sorry, T2 to T3, and T1 to T6 also is a constant pressure line. So this 0.4 is between these two pressures. Then we have another constant pressure heat addition. So this is an intermediate constant pressure line from 4 to 5, and then isentropic expansion in the low pressure turbine. Okay. So ultimately, the combustion products go out at stage 6. Okay. If you want to close the cycle, you can put a constant pressure heat rejection from 6 to 1. So in PV diagram, you can easily draw this cycle. So isentropic process from 1 to 2, 2 to 3 constant pressure heat addition at the high pressure. Then 3 to 4 is isentropic expansion in the first turbine, high pressure turbine. So we come to some intermediate pressure between P1 and P2. P4 is between P1 and P2. So then from 4 to 5 is the constant pressure heat addition, second heat addition. 5 to 6 is the isentropic expansion in the second turbine. So if the pressure ratio is, say we define two pressure ratios here, apart from the main pressure ratio R, which is equal to P2 by P1, pressure ratio of the first expansion and pressure ratio of the second expansion. Okay. So RA is equal to P3 by P4 and RB is equal to P5 by P6. Okay. So because P3 by P4 into P5 by P6, what is P4 and P5? P4 is equal to P5, right? P4 is equal to P5. We will keep this open here. Because it's a constant pressure process. So we can write this as, if we multiply these two, P3 by P4 into P4 by P6, because P5 is equal to P4. So these two terms get cancelled. So RA into RB is equal to P3 by P6. So P3 is nothing but equal to P2 and P6 is nothing but equal to P1. So RA into RB is equal to P2 by P1, which is equal to R. So R is equal to the product of the individual pressure ratios of the turbine. Okay, so overall pressure ratio is the product of the individual pressure ratios of the turbine. R is equal to RA into RB. Also, same way we can write C is equal to R to the power gamma minus 1 by gamma, and CA is equal to RA to the power gamma minus 1 by gamma. CB is equal to RB to the power gamma minus 1 by gamma. So we are defining two additional parameters, CA and CB. So because R is equal to RA into RB, so R to the power gamma minus 1 by gamma is equal to RA to the power gamma minus 1 by gamma into RB to the power gamma minus 1 by gamma. So C is equal to CA into CB, which also means that T2 by T1 is equal to T3 by T4 into T5 by T6. Okay. Now typically T3 and T5 are kept same. Why are they kept same?
Because
Blade
those
temperature.
maximum temperatures that the material can metallurgically sustain.
Correct. So say if I know that the maximum temperature sustain can be 1200 Kelvin. Okay. So and I make this T3 equal to 1200 Kelvin, but T5 equal to 900 Kelvin only. So I am not utilizing the full potential because I could have gone till 1200 Kelvin because that can be sustained by my turbine. So if I could increase the work input, heat input addition here, I will get more work output also from the turbine if I increase the temperature. So it does not make any sense to keep T5 less than T3. Okay. And obviously we cannot increase T5 greater than T3 because that is the maximum limit. So T5 ideally can be kept equal to T3, okay, maximum temperature limit. So we'll keep on continuing this discussion in the next class. Okay. Please go through the material before each of the classes so that you can go through the discussion. So first part is quite extensive and we need to go through it a little bit quickly. Otherwise, we will not be able to complete the syllabus in time. We will need a lot of extra classes. So then we will meet again in the next class. I will take the attendance directly from Teams. Stop the recording.